So thanks for coming. I'm going to switch gears a little bit on you guys, and instead of talking about how you make materials, basically something to do with materials, and particularly I'm going to talk about how we use high pressure to tune materials. But what I want to focus on a little bit is like the actual techniques of how we do this, right? The nuts and bolts of how we make pressure. So before we get too far, I thought I would tell you who I am and where I'm from. So I'm currently the group leader for our high pressure physics group at Lawrence Livermore National Laboratory. That's in California. We are a national security laboratory, which is the new word that we say for what formerly was the nuclear weapons laboratories. We're still that too. So the reason you should listen to me is I've been doing this for like 15 years or so. The reason you shouldn't listen to me is this one. I've also been a manager for about 2 years. So we'll see sort of how long it takes my actual skills to decay as I become a manager. The reason that we do a lot of pressure work really is because we are born out of the national security complex. We have enduring missions at the laboratory that engage the U.S. nuclear stockpile, assessments of foreign adversarial stockpiles, etc. And one of the key things that we need out of that is we need to understand how materials behave as a function of pressure. And so that's why we have this sort of expertise that I want to talk about. And so it's what we consider a core competency at the lab. So since we've been talking mostly about sample synthesis today, I wanted to bring up sort of where we are in pressure. I like pressure because it's a pretty fun tuning parameter. I consider it the thing that is the biggest thermodynamic parameter in the universe. I have sort of a scale here, and I've done it in gigapascals because that's my preferred unit of measurement. That's about 10,000 times atmospheric pressure. And so in the universe, it runs from something of order 10 to the minus 36, 10 to the minus 37 in sort of intergalactic space. Just empty vacuum of space, all the way up, to the other side of 10 to the 28, 10 to the 29, in the center of something like a neutron star. So this huge range of pressure. Where we live is this little dot here, which sort of expands out to this scale. This is where we'd consider sort of rough vacuum, high vacuum, things like that. We live here at atmospheric pressure. And then you have what you would consider sort of laboratory high pressure techniques are generally kind of in this region here. So they span something of order, a few GPa up to hundreds of GPa of what you're looking at. And so those are comparable to sort of ocean trenches at the low areas. So if you're talking about the hydrostatic pressure of water, up to something like, getting into the center of the Earth, which is something like 300 GPa or so. And so that's the pressure range that I'm mostly going to focus on, is how do we generate these pressures. They look very small, like they're not very much to do on this particular scale because the scale is enormous, but we are talking about things, remember, that a GPa is 10,000 atmospheres, right? So we're talking about things here that are a million times atmosphere or more that we're trying to do. I'd like to give you just a brief introduction of why we use pressure as a tuning parameter here. And the way that I like to think about this really is in terms of sort of energy and entropy. So the energetic part of pressure, I think, is actually kind of a very easy thing to think about. So if you take a material and you compress it, you're basically using energy. Think about compressing a ball or something, a sphere of gas. It takes energy for you to compress it. And so that means you're storing that energy in the pressure of the system. And it really runs out just kind of like a compressed spring here. So you can sort of use a simple 1D model of a spring, extend it into 3D, and instead of using a spring constant, you use what we consider the bulk modulus. And so the bulk modulus is an elastic property of a material, and it's basically saying exactly like a spring constant. If I go to squeeze on the material and try and shrink it, how is it going to resist it, right? If a spring has a high spring constant, it's hard to push in. If it has a large bulk modulus, it's hard to squeeze down, kind of thing. And if you put in some of the numbers here where delta is just the volumetric contraction, you can get an idea of what sort of energies you put into the system. The important thing about this is around 100 GPa, you generally put in, for typical metals or typical solid materials, something like an electron volt of energy. Right? So now basically we've added the same energy to the system by pressure that is the chemical bonding. So you can get a lot of different chemistries that happen under pressure because of this. Depending on what exactly your bulk modulus is, you may get an electron volt even much lower. So in some soft materials, because they have much lower bulk moduli and you can compress them a lot more, they can end up in this regime even at lower pressures than hundreds of GPa. This is just sort of a ballpark estimate of what you're getting. The other way to look at this is sort of the entropic states that you can access. And the way to think about this is to start with a solid, and you use Maxwell's relations for a harmonic crystal, and you just say, how do the lattice modes vibrate in the system? You can just kind of put in some typical numbers for materials here that you get. For example, the Gruneisen constant is 2 for almost every material, or very close to 2. You can calculate the entropy from the phonons, and what you end up with is this number over here, which is about 5 MPa per Kelvin, which sort of extrapolates to this here. So 5 GPa of pressure is about 1,000 Kelvin in terms of entropy. This is not an energy argument, this is an entropy argument. And so what that really means is that what you think about here is if you go to, let's say, 5,000 Kelvin, that's the equivalent of 25 GPa. What solid exists at 5,000 Kelvin? Nothing. Everything in the periodic table is melted at that point. But you can have a solid up here at 25 GPa quite easily, and so you're basically getting into a range where your entropy in a ambient pressure system, you would have melted it, so you're accessing a different phase space. Now you're now in a liquid, whereas over here you have sort of the same entropic contribution to the system, but you're in a solid. So it's an area that you cannot explore entropically without going to these high pressure states. So the main thing that we tend to do with pressure, or the first thing that we do, is we ask, what does the material do? What is its density? What is its pressure? What is its temperature? The equation of state of the material. So the equation of state was already mentioned by David earlier when talking about how you want to calculate iodine. So you use PV equals nRT. So everyone's kind of familiar with the ideal gas law. That's an equation of state. It tells you if I compress my gas, what pressure, what temperature does it go to? Things get a little more complicated for solids. So the ideal gas actually, breaks down pretty quickly for the most part at the pressures I'm talking about of multiple GPAs. There's no ideal gas anymore. But so solids behave a bit differently. I kind of tried to show this over here in terms of the compressibility. So this is the relative volume of a gas as a function of pressure in units of GPa, and then the gas here, and then the solid. So you can see the gas just basically compresses entirely. So this has gone well above the ideal gas limit. You can't even see it on the plot. It's all just tucked away down on the 0 axis, whereas a solid is behaving more linear like this over here during this range. Things get even more complicated when we have phase transitions. So one of the questions we ask is, how does the solid behave? What is the equation of state of that solid? And then it might have a phase transition, and so it has some volume collapse, and we have to figure out, well, what's the new structure? How does that behave? Etc. And things can get really exciting when you actually I don't know what happened. I think the projector turned off. I guess I've lectured for far too long already. While he's turning that back on, I'll continue talking. But the interesting thing happens when you actually do chemistry under pressure, right? So I already said that when you go to these pressures, you can get to sort of the energy scales and the entropy scales that you're doing chemistry. You're basically at thousands of Kelvin of entropy, and you're up at electron volts of energy. So you're up where you can really do chemistry. So one of the exciting new things in high pressure work is high pressure synthesis, particularly things like superhydrides. So where you take something like lithium hydride, which should be a monohydride salt at ambient pressure, stick it in a high pressure apparatus, put a bunch of hydrogen around it, and basically try and jam extra hydrogen in there. And at ambient temperature or room pressure, you can't do that. You don't have the free energy driving force, but you can get it at high pressures. And so that's one of the sort of fascinating, I think, new things that's happening. It's chemistry, it's material synthesis. I wouldn't call it low-hanging fruit. It takes a little bit of, you have to invest in your tools and things to get it to work. But it is an area that's pretty exciting. So that's sort of shown by this area down here, where you're combining these high-pressure techniques with sort of chemical techniques, interrogation of the sample under pressure so you understand what you have. And then one of the exciting things that happened was these superhydrides of yttrium here, where you can see superconductivity up around 200 Kelvin at high pressure. And so what these polyhydrides or these superhydrides are doing are basically allowing you to kind of access the purported superconductivity of metallic hydrogen, but you're being able to do it at a slightly lower pressure. These are still very high pressures. This is probably up around 100 GPa or something like that, maybe 200. Cool. So that's kind of the motivation of why I think pressure is interesting and what we're doing about it. So the next thing I want to tell you is I want to get a little bit into how we make pressure. I'm not going to talk about all of these techniques, but I wanted to put this up here just as an idea of the different tools that you use to make pressure. So some of you may be familiar with cryostats, and there's various cryostats. A dilution refrigerator that gets you to 5 millikelvin or 5 microkelvin, right? You have a helium flow cryostat that gets you to 4. You've got a furnace that gets you at 100, right? So you have all these different tools to get you to different pressure, different temperatures. Similarly, under pressure, we have different tools. They're generally in the community are bulked into static pressure generators and dynamic pressure. Static pressure is what it sounds like. You basically clamp pressure on there, so you can apply a pressure and it stays put. So examples of that are, some of you may have used a clamp cell or seen a clamp cell. This is kind of like or a die press. If you've ever pressed a pellet to make a sample, you're basically looking at something like a clamp. A Bridgman cell is very similar. It's basically opposed anvils, and then what I'll talk about later in a little more detail, which is kind of my specialty, is the diamond anvil cell, or the DAC. And so this is sort of the region of phase space that you can explore with these different tools. Clamp cells are generally limited up in the sort of the 1 to 2 GPa range. Bridgman cells get you up maybe to 10, and then diamond anvil cells are up to maybe, right now they're getting us up to something like 400, 500, 600 GPa. So if you tend to be stuck in temperature space for these. It's very hard to heat clamp cells because they're gigantic, and they tend to break when you do that. Same with diamond anvil cells. Eventually, as you heat them, you just got this big pile of metal and screws, and it just breaks. And so one of the ways of getting higher temperatures and higher pressures is then to go to this dynamic pressure regime, which I'll talk a little bit about, but I'm not going to spend as much time on. There are what we call gas guns. There's the pulse power facility, which is basically Sandia's Z machine at the Sandia National Laboratory in Albuquerque. At Livermore, we have what's called the NIF, the National Ignition Facility, which is a gigantic short pulsed laser that can be used. And then there's also things like high explosively driven flyers or compression. So basically you can blow up something and look at what happens to it. So these are naturally not static, so the experiments are over quickly. So they generate very high pressures, very high temperatures. Your sample is generally gone, this one especially, where you literally explode a high explosive around it. There's nothing left of your sample. And so while these you can interrogate things pretty well, you can add leads, you can look at spectroscopies, you can do all those things. These are a little more difficult because this experiment can last as long as you need it. This one is over in maybe a few nanoseconds. If you're lucky, it's a few microseconds kind of thing. But that gives you this access up to these higher pressure ranges, so up into the 10,000 GPa type ranges for some of the short pulse lasers. Now the short pulse laser experiments are over, well, they're done in a nanosecond. Yeah, I'll talk a little bit about that. We measure a lot fewer things, obviously. There's only so many things you can measure there. So because I don't do it as much, I'm going to start and talk about dynamic pressure generation. So the way that we typically do this, this is the realm of what we call shock physics. And you can generate an exquisite equation of state with one notable exception: we don't get the temperature. And the reason we don't get temperature, but the reason we get an exquisite equation of state is because we use what are called the Rankine-Hugoniot equations. So this is a fancy name for conservation of mass plus conservation of momentum plus conservation of energy applied to a shock front, which is nothing more than a wave moving through a material. So in the case of a shock, it's a wave that's moving through the material, but it's faster than the speed of sound in a material. And so once that happens, you generate this shock front. A shock front then will break out of a sample along this trajectory here, which is called the shock Hugoniot. Sometimes in old literature, this is called the shock adiabat, especially from Russian literature. But it's this sort of brownish, yellowish curve here. And what that is basically is it's a locus of points that says if I hit it this hard, it's going to end up in this state. If I hit it a little harder, it's going to go to that state, a little harder to that state. So one thing you can see quickly from this is it peels up. And it sort of asymptotes. It doesn't go any further. So this is one of the challenges with shock physics, is that you get stuck making, eventually you get stuck making temperature and not making pressure. This is the phase diagram of water, by the way. But the nice thing about that is because you have these three conservation laws that are in here, they're written in terms of shock speed, basically sample speed. So this is your impact speed. This is how fast your sample goes, the initial density of your sample, the density you get to, and the pressure you get to. And you have 3 equations here, and you have 5 unknowns. So you just have to measure 2 things to get all of those things done. So what we typically measure is the shock speed and the particle speed. So the particle speed is basically how fast the sample moves. The shock speed is how fast the impactor hits it, so this is a bullet hitting a wall, and then the UP on the backside is basically how fast the wall moves after it gets hit by the bullet. And so these can generate very nice equations of state with well below 1% uncertainties in these parameters here, but not in temperature, because I've not done anything to tell you where my energy went. I've conserved energy and I've told you what the total energy is, but you're making pressure energy and you're making thermal energy. So how that's equipartitioned is not described by these equations. So how we typically do this in a modern setting is with what's called the two-stage gas gun. So a two-stage gas gun is a pretty cool thing to see just because it's a gigantic gun. On one end you have a breech and you have a piston or a bullet. You basically fill up your rifle barrel here with hydrogen gas, and you literally fire off a breech just like if you were on a Navy ship or something. There's a big powder explosive that goes off and it runs this piston down. So it runs the piston down and compresses all of this hydrogen gas up against something else, and that something else is then a smaller rifle barrel. So all you're basically doing here is amplify. This is a rifle amplifier, right? So I start with a big piston that I push on here. I'm going to compress all of this gas, and then I'm going to basically hit this here, this second impactor, with a pressurized gas. This gas is going to have more energy than the breech that we put in, and we're going to put it through a narrow channel. And so this piece here is going to go even faster than the first one. So sometimes we call this the piston or the sabot or other things. It has all kinds of names, the bullet. This guy goes at sort of typical high-powered rifle type speed, so a kilometer per second. This is literally like a gun that's on a Navy boat or something like that. And then the second stage amplifies things by something like a factor of 10. So these get up to something like 10 kilometers per second. And then this impactor is going to hit our target, and we're basically going to measure things after that. And the 2 things we need to measure for sure are the US and the UP, the shock velocity and the particle velocity. US comes from the impactor, so all I need to know is how fast is the impactor going. There's lots of ways to measure that. You can put like 2 pins here that it sort of shorts when it goes through. You know how the distance of it. It shorts again when it comes back, and so you can basically pick up a transit time and know the velocity. That one's not too hard. The challenge then comes with measuring the target. So this is what a gas gun looks like. Here it's this nice long rifle barrel. This is probably maybe 40 yards or something like that for this particular one. Let's see if I can play. I have a movie here of what it looks like when you fire your projectile. So that's your projectile hitting your target. So you see your projectile is completely gone. That was a piece of plastic. It looked like rubber, but that was a solid piece of Lexan that basically just liquefied and blew up and exploded. So this here is why you don't get to come back and get your sample. There's really nothing left of your sample when you're done. So the way that we measure this, there's a few different measurements that can happen. So this is sort of the key. So I've generated the pressure conditions by throwing a shock at it. Now what do I want to do? The first thing we usually do is we need to measure, like I said, US and UP. So we need to understand the shock state. If I just throw a material, if I throw an impactor at something, I generate a state, a pressure temperature condition, but I haven't measured anything. I don't know what it is. And so the way that we do that is usually with something, it's velocimetry of some type or another. So we use things like pin timing, so we can ask when to, like similar to the shock or the impactor coming through, what's the transit time? So we can do things by having clever sort of sample geometries so that we can understand how long it takes the shock wave to pass across the sample. Requires very good metrology of the sample beforehand, but it's a simple method. All it is distance over time kind of things. And so these give you these wave traces that you find like this. And so this part here, let's ignore this part, but the flat part on the top is basically the shock physics part. So you've shocked the material up, all of a sudden it wasn't going fast, now it's going fast. And so that's your number that you're going to pull out through this. This particularly is a velocimetry trace. So this is basically a radar gun is all you're asking here. So that tells you your pressure condition that's fine, or your density condition, but you might also want to know what your temperature is. And so your temperature, the way we try to measure that, which is very challenging, is to do thermal emission. So this is looking kind of face on at a material here. And you can see here's where the shock is. This over here on this side is just an edge of the material that you can ignore. But what you're looking at basically here is black body radiation coming off. So we've hit this thing, it's going up high in temperature, so it's emitting. Right, all it's doing is shining because it's hot. And you can measure the wavelengths that are coming out, and you can try and back out the temperature by that. Another thing that's happened in recent years is the synchrotrons, the X-ray sources, have become much more powerful. So you can basically shine synchrotron light on your sample as you're doing it. So this is an example that's a little bit different. What you're looking at here are glass spheres that are being shocked. So the shock front comes in here, and then you see the time steps as they go here. And what we were trying to understand with the science of this one is kind of basically how do these spheres crack, compact, break apart? How do things happen? If I have a bulk piece of material and I apply Rankine-Hugoniot equations, that's fine. But once I take away the bulk material and I ask, what is the speed of sound? That's the important thing. What's the bulk modulus of sand? Right? Well, I don't know. It's just sand on a beach, right? You can push on sand with your foot and it makes a hole, right? But eventually it stops making a hole and it pushes back. So there's this compaction regime. There's this regime where it behaves as a heterogeneous media before it kind of collapses into a homogeneous media. And that's what we were trying to understand here. And so all this is basically imaging with X-rays. You can also do diffraction, pretty much any other thing you want. If you can shine X-rays at it and you can detect it, you can do it. Spectroscopy has become pretty hard here simply because of collection times. So normally if you shine some photons in on something, you may shine 100 photons in. With something like diffraction, you get a lot of photons back. With something like imaging, you get almost all the photons back. But with something like spectroscopy, you're getting 1 out of every maybe 10 to the 4 photons back or something like that, or maybe even fewer. So spectroscopy isn't done quite as much in this, or that's sort of something we're working on as a field. So that's all I wanted to talk about in terms of dynamic pressure. So I wanted to move on then and talk a little bit about static pressure. So the principal concept of static pressure is actually fairly simple. All you're doing is making pressure by applying force over an area, right? That's what pressure is. In the case of a clamp cell, you do that usually by having something that's maybe several millimeters tall, maybe it's a millimeter in diameter and it's 10 millimeters tall or something like that, and you just apply pressure to that thing. So the problem with applying pressure to something of that size is it wants to explode outward. So the real trick in doing any of these pressure generation devices is how do you keep something that you want to crush this way from exploding outwards with Poisson's ratio. And so with a clamp cell, you basically just put this gigantic belt of metal around it. And so that keeps it from pushing out. The diamond anvil cell does effectively the same thing. Its belt of metal is what we call the gasket. The gasket's actually a fairly thin piece of metal. It's about usually like maybe 200 to 400 microns thick. And in this dimension, it needs to be something like probably half a millimeter in that dimension. The reason it's that size is not because there's anything special about this material. It's serving the same exact purpose as the belt on a clamp cell. It's that the working area that we're going to use inside is now 100 microns in diameter and 40 microns tall. Whereas the clamp cell, we're millimeters on a side and multiple millimeters tall. That means we need centimeters of material on the outside to hold that pressure. So the real trick of the diamond anvil cell is the A part. Right, I'm taking A and I'm making it very small, which allows me to generate high pressure. So the way you do this is basically you take 2 diamonds, these look just like an engagement ring diamond, and you just put them point to point and you push real hard. So you get another advantage by using diamond. You could imagine doing the same thing with a piece of plastic, right? But you're not going to generate very much pressure because your plastic is going to fail, right? You're going to put a load, you're going to put force on the plastic. Mechanically, you're going to exceed its yield strength and it's just going to die. What we get from the diamond is we're allowed to put a lot of force on it because it has a high bulk modulus and it has a high elastic modulus, which means that it has a very high yield strength. So we can push on it a lot before it fails. So your limiting factor for generating pressure is generally, how much force can you put on it before it fails, and then how small of an area can you make and it stay there. So we use hard materials for this. There's other gem anvils. People have done sapphire anvils and things like that. But in general, you need a hard, what you would consider a hard material. You can also use things like tungsten carbide here. Some of the metals will work, but they end up yielding and having a sort of a plastic flow that limits them down to maybe, I don't know, maybe like 6 GPa or something like that. We use a metal gasket. Again, we want a hard gasket. This is the same as if you wanted to build a clamp cell. You'd want to build a clamp cell with a hard material so they can hold up to the force. In the sample chamber is where our sample goes. Again, the sample chamber is 100 microns wide or so. So to put that in perspective, that's about maybe 2 or 3 of your head hairs wide. And it's about 40 microns thick, so 1 head hair thick is what's left. Put the sample in there, we put a pressure transmitting medium. Sometimes the sample can be its own pressure transmitting medium. For example, if you're interested in studying neon, just put neon in there, that's fine, it's great. It's a pretty good fluid. And we also put a manometer. So a manometer is a nice fancy word for a pressure measurer. There's a couple of different ways you can measure pressure in these. You can use ruby is a very common manometer. So with ruby, you put it in there and you shine a laser light on it and the ruby will fluoresce. The fluorescence line of ruby is in the red spectrum and it shifts very uniformly with pressure. So it becomes it's a calibrated measurement in that sense. Other manometers you can use are also, because we do a lot of X-ray diffraction work, you can use standards like gold or copper are very good standards, tantalum sometimes. So you put another metal in there that preferably is not going to have a phase change. And you can then find the X-ray diffraction lines which allow you to find the volume of the material, which allows you then to find the equation of state. Basically from the equation of state you can extract the pressure from the volume. Some of the original metal sort of things like gold, the gold equation of state, are actually developed from shock Hugonio measurements because those have the conservation of mass, momentum, and energy. So you get that measurement from a shock measurement and then you basically temperature deconvolve it down to give you an equation of state for the metal. So that's how you ended up getting some of the first manometers, was by taking the shock equations and then mapping them back onto a static platform. A lot of the things that we end up doing here with diffraction, we do at the X-ray sources. So we mostly, in my group, we end up going to the Advanced Photon Source, which is in Argonne National Lab outside of Chicago. You can go to any synchrotron and do this if you want, for the most part. All you really need is a tight beam that will come down and hit your sample, and you need some detectors and things like that. So we have done other measurements at SSRL. We've done things at the Advanced Light Source. The ESRF has a dedicated beam line for high pressure, so does Spring 8. So this is sort of a routine thing at synchrotrons. The key things you really want are these micro-focused beams. Again, the sample I told you was only like 100 microns. So if you have a 1 millimeter beam and you throw it at a 100 micron pinhole, you've thrown away 99% of your beam or something. So you need to be able to shape your X-ray beam and focus it down into something so that you get all of the photons that you've got from the synchrotron. But there are, like I said, there are dedicated facilities to this, so it makes it a lot easier. If you had to do this in the early 2000s, you had to basically build that facility, so it's much harder to do. I didn't have to do that, so I just use it. Well, I did use it. And so here's an example of data we get. Fazel, you'll recognize this one. So we basically, this looks exactly the same as your normal diffraction patterns that you get on a theta 2 theta geometry. So if you make a sample and you want to check if your sample is good, you're going to put it in a diffractometer and you're going to look at the lines, right? So the only difference that we have at the synchrotron generally is we go through the diamond anvil, so we're doing it in transmission rather than reflection. There's a couple of advantages that you get from doing the synchrotron then. Is one is you have a lot of photons, so you can go through a lot of material, and you have high energy photons, so you can actually get through materials. Most of the time when you're sitting in your lab source and you've grown this beautiful single crystal that's 5 millimeters by 5 millimeters by a centimeter, you can't get X-rays through it. And your visor doesn't want you to carve it into little tiny pieces to do transmission X-rays, so you do reflection. In our case, everything is small, so we do it in transmission. The high energies also take everything. If you're used to looking at diffraction patterns, we tend to run things at about 30 kiloelectron volts, so that's about 3 times higher than copper. And so what that means is we go out to something like 22, 24 degrees in 2 theta, but if you expand this out and sort of map this onto the copper diffraction lines, this goes out to about the equivalent of 90 degrees or 100 degrees or something like that. So by going to the high energies, you compress your scattering cone from a 90 degree scattering cone or a 120 degree scattering cone down to something that's about 20 degrees. So it's actually helpful for the geometry of the diamond anvil cell as well, and because we're kind of aligned along that compression axis. But this is what you end up with, diffraction lines. If you've looked at diffraction patterns, these look like diffraction patterns. In this case, we have a sample of lanthanum bismuth and its low pressure phase here, and then there's some little tick marks here in blue, which are copper, so that's our pressure standard. So we basically, it's FCC, it's cubic. You have plenty of lines that you find here, so finding its lattice parameter is very easy. You can find it to very high degree of accuracy, and then from that we calculate the pressure. The other thing you can see is neon in this. So in this particular case, we loaded neon as a pressure transmitting medium, and you might say, well, neon's a gas, why does it diffract? We're at 7 GPa now, and so neon is a solid at that point. At 4.7 GPa, neon solidifies at room temperature. So everything above that, it's actually quite nice because your pressure transmitting medium is also another pressure calibrant that you can use. So it's these green lines that you can see here. So as we go up to higher pressure, then we find a phase transition. We still have our blue and our green lines, so that's our copper and our neon. Those don't do anything special. They're both cubic, so they just kind of roll up with pressure. And then we have these new lines that we find. And so from that, we can actually do, we can measure a lot of these diffraction patterns here. We can extract the volume as a function of pressure, and we can then identify the high pressure structure and extract its volume. So these are theoretical calculations done with DFT that match up exceedingly well with the data here. And so you can see the data as the open dots, and then the DFT calculations are running through as the theory. So doing an excellent job. This is an interesting system that goes from what's a rock salt structure. So it's really very simple, right? It's just two elements, lanthanum and bismuth. It starts as a rock salt structure, so that's FCC, so it looks just like sodium chloride, table salt, and it goes into a body-centered phase. It's not BCC because it has 2 atoms, so this is basically the cesium chloride structure. So these are basically 2 classic salt structures that happened here. And so this is a common thing to see in high pressure physics. So the next thing so that's kind of how we do the structure part. So that's the first thing of what you want to understand, right? Of any materials physics problem, what do I have? You know, this was your chemistry, right? It's a unique set of elements and the structure. We have to determine that. So we determine that in the static sense. Then the next thing we want to look at are properties. So again, if we're asking materials physics questions, we may say, well, what does the material do while it's in that state that we've generated? And there's a few different techniques that we do, and I'll kind of walk through these until we run out of time or get tired, and we'll see where we get. But spectroscopy is one. We've done a lot of electrical transport, and then we've also done small angle X-ray scattering. And just in general, what you can get out of these are sort of what I like to call off-axis measurements. I'm an experimentalist, so I consider my job to prove a theorist wrong. Every once in a while I succeed, and sometimes I fail miserably. And so one question you may have back in this slide is, okay, so the theory got it right. Did it get it right for the right reason? Right? There's a few different parameters that you can tweak in your DFT model, and yeah, you matched the data, but did you match the data and match the physical properties, right? Is this an insulator or a metal? Does it have the right valence configuration? So these are what I would consider off-axis measurements that are generally harder to do, but things that we can do. So spectroscopy is a good one because you can ask, what's the valence of the material? You might see a phase transition and something like a rare earth goes from a 2+ to a 3+ state. And if your theory predicts your equation of state perfectly but doesn't get the valence transition, then it's doing it right for the wrong reason. And that means it needs to be refined. Similarly, you may have something where you have a magnetic state that gets destroyed in favor of a non-magnetic state. And again, maybe the theory says, oh, I got the volumes and the unit cells perfect, but I didn't get any of the magnetism right. Again, it needs to be refined. It's not exactly reproducing things. I think I'll talk about that, but they're special anvils. So let's talk about valence first here. So this is particularly a compound that I've chosen to sort of highlight what we're doing here, and this is ytterbium, nickel, indium-4 or gallium-4. And so it's even at ambient pressure, this has a mixed sort of ytterbium valence, but under pressure it's predicted that the valence will sort of smoothly increase as you collapse the unit cell or as you close the ytterbium spacing. So if you apply pressure and move the ytterbium atoms closer together, you should get a valence increase. And so we made these samples with a cell flux technique and we put them in a DAC. In this case we used a beryllium gasket. And the reason we use beryllium is because it's a pretty good, pretty stiff metal. It's by no means the stiffest metal on the periodic table, but it's the second metal on the periodic table, which means it doesn't have very many electrons in it, which means it's very transparent to X-rays, especially the X-rays we're looking at, right? I'm using diamond as my anvil. The beryllium is more transparent than the anvil itself as far as X-rays are concerned. You know, visible light photons, right, it's a metal that they fling off, but X-rays go right through it like it's not there. So that allows us to bring X-rays in through the diamond cell here. We've loaded our material in the sample chamber, and we can collect then the fluorescence of the material coming off with a spectrometer coming out through the beryllium gasket. And so what we're doing in this particular case is we're looking at the valence of the ytterbium atom. And so we have a ground state here that we shine a photon into, and we excite a 2p electron out into the conduction band. This is not particularly a resonant experiment right now that I'm talking about, but we excite the electron out, and then that gives us sort of an intermediate state configuration that's dependent on the valence, whether we have 3 plus or 2 plus here. And so basically there's a splitting now that happens whether the atom is in the 3 plus state or the 2 plus state, and then these decay down out of the D states to fill this hole. This is called the Lalpha emission, and you basically get one that's for the 2 plus state and one that's for the 3 plus state. And what you see then on a spectrometer is you see something that looks like this, where you have a peak. So you have a 3 plus peak that's over here, and then you have a 2 plus peak over here. In this case, this is samarium hexaboride under pressure. So that's one of the old dogs that has new tricks. So with the ytterbium sample, we did basically the same type of measurement here. And so you can see, similarly as a function of pressure, you've got sort of a 3 plus peak and a 2 plus peak. There's some details in how you fit this that I don't want to go into. But what you can basically see then is that you've got a change in this peak structure, right? As we go to higher pressure, we get more of this 3 plus character, and the 2 plus character sort of in general goes down. So we're changing the valence of the system as a function of pressure. We can do this in a resonant fashion as well, which is shown here. So what I showed you here, this spectrum is basically hidden along this line. So if you were to map the intensities along this cut that goes right through here, that's the exact same spectrum I just showed you, no difference. But what this technique allows you to do is actually go kind of off axis of these. So all you're doing is changing your incident energy in addition to your pickup energy that you have here. It's plotted in this sort of weird way to get it into transfer energy, which looks like this. The important part about that, the nice thing about that feature is then you can kind of look and see if you have tails that come off here that are flat in this transfer energy term on the low side, and those are like real valence states, as opposed to being sort of artifacts from some other quadrupolar transition or something weird like that. So the only real information we're getting out of this particular measurement in this case is just confirming of what the peaks really mean. It's just a lot of work to confirm that the data seems to be correct. And so this is where we ended up with the data. This is the DFT prediction. It basically doesn't really care if you have ytterbium nickel indium 4 or ytterbium nickel gallium 4. In the DFT calculation, all the indium and the galliums are doing are setting the spacing. They're just setting the unit cell, setting the lattice parameters. So they're chemical doping, that's all they're doing. But in the data we can see we have structural data as well. I didn't show it in this, but we do have all the structure data. And we have the valence data. So one thing is apparent is that there's no simple continuity between the two, right? So if you start over here on the indium side, you kind of ride up in valence. The slope is nominally correct, but it's a little bit off. But then there's this big precipitous drop. So even at the same unit cell volume with the ytterbium nickel indium, and when you go to the gallium version at the same lattice parameter, you have a very different valence. So it means that the galliums and the indiums are doing something chemically. They're not just inert bystanders. And this is an example where the DFT is getting a lot of the physics right. It's getting a lot of the structure right, but it's not getting the valence right. It's not actually capturing how the ytterbium is interacting with the gallium or the indium in that case. And so this is one where we were happy that the theorist got it a little bit wrong, but he did do pretty well. He got this pretty darn good up here. You gotta give him credit for that. And so this is the good part about this sort of measurement is it can drive you to improve your model, right? If you really care about predicting what this material does, you haven't got it all right yet. So it drives you to do that. And if you didn't take these spectroscopic measurements, you may say, oh, well, it works. It reproduces the lattice parameters fine. So I'd like to talk a little bit about magnetism next. In particular, this is going to be a story about electrical transport in a diamond anvil cell. Magnetism is a very hard thing to measure under pressure. When you're sitting at ambient pressure and you make your magnetic material and you put it in your squid, you get this beautiful measurement. It's an easy measurement. You stick it in a straw and you put it down the little tube and you come back a few hours later and you have a great measurement. It's a very sensitive instrument. But if you've ever used the squid and you put tinier and tinier samples in there, it gets harder and harder to get a signal out. And if you put your tiny sample, like maybe it oxidizes and you encapsulate it in something, it gets even worse. And so that's what you've done with a diamond anvil cell. So you can't just take a diamond anvil cell and stick it in a squid and get good data, basically, because you've encapsulated it in a bunch of stuff, particularly magnetic stuff, and your sample's really small. So we needed another technique. So what we're going to turn to here is using electrical transport to do that. So I'll talk a little bit about that. The sample I want to talk about is uranium antimony 2. That's sort of the highlight of this technique here. It's an antiferromagnet at room temperature, or at room pressure, excuse me, of about 200 Kelvin. So it's relatively high AFM state for uranium. It has, quote unquote heavy electrons, heavier than a not heavy electron, but I wouldn't call it a heavy fermion system. It's not quite that heavy. There's something going on, but it's by no means holding any records. And it does have some transport anisotropy as well. So I'm not going to talk about flux growth because I'm sure everyone else has talked plenty about that. But this gets to your question, Jack, as to how we do these measurements. So we used what's called a designer diamond anvil. So we take the diamond and we put metal microprobes. We tungsten sputter deposit these along the sides of the diamond. And then we come back in and we grow diamond on top of those, which now encapsulates those microprobes. So we do that with a CVD technique. So I now have a diamond that was pristine, polished from the ground. I've put microprobes on the sides of it, and then I've coated it again with diamond and made it and coated all of that. We then come back and repolish everything so it looks like a diamond anvil instead of like a blob. And what happens is these microprobes get exposed only at the tips here. So all of this that you see here is kind of going down and away from you in the board. So it's going back into the board and it's underneath diamond. So if you were to come and touch that part there, all you touch is diamond. It's a flat surface of diamond. You can just see through it and see the microprobe beneath it. If you touch right at the tip where that line ends, that's exposed, and that's a piece of metal that's right at the tip of the diamond, right flush with the surface. So what that allows us to do then is put a sample in contact with those. So basically just plop a sample right on top of there. We usually backfill with some sort of pressure medium. In this case, it's a steatite, which is soapstone or chalk, basically. It's a very soft, mineral. And you can see the sample is sitting there. Underneath it are the microprobes that are emanating. The nice thing about this technique, number one, is the microprobes are there. I don't have to do anything with them. The diamond just came with them. Now, we had to do a lot to make the diamond, mind you. But after that, it's just they're there. And it's no longer going to short to the gasket at all, right? So my sample is in here, and you can kind of see that the sample touches the corner here a little bit, but that doesn't matter. So the gasket is a metal. It's sitting on the diamond, which is an insulator. That's the only thing it's touching, and it's touching the sample. So if you're a current path, the current is going to go through the sample. And it's not, I don't even care if it goes here and it runs around the gasket for a while and comes back and goes through the sample. It doesn't matter to me. It's either not going to do it, or it's going to be irrelevant. So it allows us to get away from one of the common problems with diamond anvil cells, which is your leads shorting against your gasket, basically. And especially as you put pressure on something and you have these leads, sometimes people will take things in the gasket and sort of make grooves or put an insulator around it, and then they put the leads on top and they smush them into there. But as you apply pressure and there's shearing forces, you either shear the lead off or you just push it through the insulating boundary and then you short to your gasket. And so your measurement can become much more challenging. So that's how we do this. We call these designer diamond anvils. Sort of the electronic configuration looks like this. We generally put current through these two opposing leads, and we'll measure voltage across here, so that gives us something like a Hall voltage, and then we'll also measure voltage along this direction. So we have a 4-probe measurement in both cases, and we have one that's parallel to the current and one that's perpendicular to the current. The other nice thing about this geometry is this geometry is fixed. Right, so this was made by a sputter deposition technique. So these really are fairly perpendicular across the sample, as opposed to if I just did it kind of by eye and with silver paint underneath a microscope. They're actually pretty good. So there is leakage sort of from the channels. It's not a perfect Hall bar or anything like that, but you get a pretty good measurement from that. So this is an example of what we see from electrical transport. We start here with our sample at ambient pressure. We apply pressure. The Tn goes up. So the nail transition is that kink, that knee. It goes up with pressure. Then all of a sudden it disappears, somewhere around sort of 8 to 10 GPa. And we see this other transition here, which is not Tn. It's something different. It has a completely different pressure dependence. If you kind of watch it, it's now going down. So I have something that's going up with pressure, and then a phase transition, and something that goes down. If we look over here, this data is at 14 GPa, so somewhere between that one after this purple one. And we apply magnetic field. We look at the transition, and basically we don't see any change. So magnetic field is not suppressing this transition. It's just constant. It stays at the same temperature at magnetic field. So what we then did to look at the magnetic state is to look at the Hall effect. Particularly, we wanted to look at the anomalous Hall effect. And so in your normal Hall, so this is sort of if you had just sort of a conventional sample, right? You build your room pressure sample. You have some sort of conventional Hall effect over here. You just have a slope. It's a metal, fine, right? It has a slope that's related to the carrier density. If you have a magnetic sample that's also a metal, you'll get this, but you'll also get the anomalous Hall component. So basically, the magnetism of the sample is getting mapped into the field that the sample's actually seeing. And so what that does is it basically puts the hysteresis loop that you would get out of a squid into your signal as well. Now, not everything has hysteresis. In fact, most things don't have hysteresis, and so you won't necessarily see this large gap, but you do see something where you conflate these two behaviors. So you have something where there's a slope out at higher field, and you have something where you have curvature down at low field that's due to the fact that your sample has a magnetization inside of it. And so that extra term is the anomalous Hall effect. This one's kind of easy, and it takes care of itself. The anomalous Hall effect is pretty cool in that it's proportional to magnetization, but its proportionality constant is this RS term, which could be almost anything. So that's the problem with anomalous Hall effect. It's great to pick something up, but it's very hard to say exactly what you are in terms of magnetization. So if we go to look at the anomalous Hall effect, this is what we see as a function of temperature. So here's low pressure data. So this is in like phase 1 where it's an antiferromagnet. This is high pressure data where it's in phase 2 where we don't know what it is, but it's not the same phase. And so there's some interesting things that sort of become apparent right away. You start warm here at the low pressure phase, and you have a slope. And then as you cool down, you get a slope change, number one. And so there is a known reconstruction of the Fermi surface in this material that happens when you go antiferromagnetic. But you really just see lines here. This line maybe stinks and the data's not as good, but you just see lines. When you go to higher pressure, the first thing that comes out is you basically stay with the same slope. You don't ever change slope as a function of temperature. But if you start out at higher temperatures up here, as you cool down, you develop this curvature that shows up. And so that's the anomalous Hall component creeping in to the signal. You can plot this up over here. So what we do is we take off the linear term at high field. So we're left with nothing. All we're left with is the anomalous Hall term. So all we've done is subtract that term off of the measured data, which is that. And so we're left with the anomalous Hall term. You can plot this up as a function of temperature, and you see as you cool down, you basically are generating this extra anomalous Hall term, plot that up then as a function of temperature, and you have what looks like an order parameter. And particularly you have something that's not terribly far away from an order parameter for a ferromagnet, with the caveat that I don't know exactly how I'm converting this from an R measurement, a resistance measurement, into a magnetization measurement. There is a proportionality constant that's in there that can be temperature dependent as well. But so what this allows us to conclude from this, and what we did conclude then, is that this is a ferromagnetic transition. So under pressure, we went through a phase transition, and we destroyed antiferromagnetism in favor of a ferromagnetic system. And And that allows us to develop an entire phase diagram from this, from the electrical transport. So you can see the data points that we get from defining the nail transition, and then the data points from defining T0 is what we called it. Yes, there is a structural transition here. So at the time we didn't know because we weren't doing structural measurements, we were only doing electrical transport measurements. But there is a structure transition that goes here at about 9 GPa or so. It goes from an orthorhombic tetragonal phase here to an orthorhombic phase over here. We're still working on exactly where the atoms are. It's kind of a bear of a structure. But you see that T0 goes down. So in this case, you can say T0 is Tc. That's the Curie temperature. It goes down. It disappears. It just abruptly disappears. And so there is data up here. This green stuff is real data. That's the slope. This is the local slope of the resistance, otherwise known as the derivative. And it's a power law derivative. But we have data here. We just have no transition. There's no anomalous Hall component up there. So all the Hall signal is flat. And we don't see a transition in terms of, we don't see anything in the resistance like a change in slope or any like a kink or a knee or anything like that. So it really does just sort of abruptly die somewhere between here and here. It just goes away. So, you want to stop?
Sure.
Okay. So I'll skip this part. If someone's interested, we can talk about it later. But it's getting after lunchtime, so I'll stop there.